Hi, this is the first lecture on Chapter 14, Rational Functions. So, when we talk about a rational function, we should probably start with the definition. So, a rational function is just defined as some function r of x that's equal to a function p of x over q of x, where these two functions p of x and q of x are polynomials, and q of x is non-zero. So we've talked about polynomial functions in the previous chapter. So remember, polynomial functions have to have real number coefficients, a single variable x, and exponents that are positive numbers. Now, just to refresh our memory, that a constant still counts as a polynomial. So like 7 over x is a rational function because 7 is a polynomial and x is a polynomial. But that's the gist of it. So the first idea that we want to talk about is determining the domain for a rational function. So hopefully you remember from when we talked about polynomials that the domain for any polynomial is all real numbers. The problem of that is that we have one polynomial divided by another polynomial, and we know that we can never divide by 0. So if the denominator, the polynomial in the denominator of this rational function, can equal 0, we can't get a value for, in this case, f of x, if that's the case. So to figure out the domain, all we're going to do is we're going to take the denominator and set it equal to 0. So if I add 1 to both sides and divide by 2, I get 1/2. So for my domain then, what I'm going to have is negative infinity up to 1/2 union 1/2 to positive infinity. Remember that the parentheses mean that that value is not included, so it's everything below 1/2 and everything above 1/2, not including 1/2. That's what we've written here. And that's the gist of it. Let's do an example that's a little bit more complicated, but not so much so. So we want the domain for 3 minus x over x cubed minus 4x. So again, I'm just going to take the denominator and set it equal to 0 and solve. In the previous chapter, we talked about solving polynomials that look like this. So first thing I notice is that this polynomial is factorable. There's a greatest common factor of x that I can take out. And then I notice that x squared minus 4x is factorable. That's the difference of 2 squares. So it can factor to x minus 2 times x plus 2. And then I just take these 3 factors and set each of them equal to 0 and solve. So I'm getting 0. When I add 2 to both sides, I get positive 2. When I subtract 2 from both sides, I get negative 2. So my domain then is negative infinity up to the smallest one, negative 2, union negative 2 up to the next smallest one, which is 0, union 0 to the biggest one, that's 2, union 2 to positive infinity. So again, the domain is long, but that's not really very difficult, right? We just have a blank space every time we get to one of these values where that gives us a 0 denominator. You know, so that's not too bad. What we're going to transition to now is trying to draw the graphs for rational functions. To do a good job with that, we need several things. We need vertical asymptotes. We need end behavior / horizontal asymptotes. We need the zeros for the function, and we need the y-intercepts. Just FYI, zeros and x-intercepts are really the same thing. You could use those terms almost interchangeably. The only difference is zeros includes imaginary things and x-intercepts wouldn't include the imaginaries, but close enough. So these vertical asymptotes, how do we find those? I'm going to abbreviate vertical asymptotes as VAs. We're going to vertical asymptotes are going to be of the form x equals k, where k gives a 0 denominator, but not a 0 numerator. These end behaviors, this is kind of tricky. We're going to do more of this later. We'll come back to that a little bit later. Oh, I lied. I'm going to do it right now. So there are 3 cases here. In the first case, if the degree of the numerator is greater than the degree of the denominator, do we remember what degree is? That's just the largest exponent in the polynomial. Okay. Then the end behavior, again, I'm abbreviating end behavior with EB, will be y equals q of x, where q of x is the quotient of the long division between numerator and denominator. If the degree of the numerator equals the degree of the denominator, then the end behavior will be y equals a of n over b of n, where a of n is the leading coefficient, LC just stands for leading coefficient, of the numerator, and b sub n is the leading coefficient of the denominator. And the third case, if the degree of the numerator is less than the degree of the denominator, then the EB will be y equals 0. Okay. The zeros are values x equals h, where plugging h into the numerator gives you a 0. But not a 0 denominator. And then the last thing, oh boy, okay. And the last thing is the y-intercept, and that's easy to get. It's just the value when x equals 0. Okay, so let's do a little example and show you kind of how to get these pieces of information and how this kind of all works, because that was a lot all at once. So let's say we wanted to graph y equals x minus 1 over x squared minus 4. So the first thing that I want to do is I want to factor the numerator and denominator. So the numerator is prime already. There's nothing to do up there. The denominator, I notice, can factor. It's a difference of 2 squares. In fact, we factored x squared minus 4 in our earlier example to x minus 2 times x plus 2. I notice nothing is going to reduce from the numerator and denominator, so we're all set there. So let's find the vertical asymptotes first. So I can get those by just setting the things in the denominator equal to 0. And solving to give me vertical asymptotes at 2 and negative 2. The next thing we'll look for is our end behaviors. So the degree of the numerator is 1, because I just have an x to the first. And the degree of the denominator is 2, because it's an x squared. And since the degree of the numerator is less than the degree of the denominator, we just have y equals 0 for our end behavior. Next up are the zeros. I get those by setting the numerator equal to 0 and solving. So this tells me that I have the point 1, 0, or the graph crosses the x-axis at the point 1, 0. And then the y-intercept, if I take x equals 0, that gives me y equals 0 minus 1 over 0 squared minus 4, or just 1/4. That is then the point 0, 1/4. So let's go ahead and translate this onto a xy axis, this information. So let's try to make that a little straighter. I'm not sure that was any straighter. Okay, so the first thing I'm going to do is draw in my asymptotes and end behaviors. So I have vertical asymptote there at x equals 2, or negative 2, excuse me. And another one here at x equals positive 2. And then I have a horizontal one here at y equals 0. I have the point 1, 0. And I have the point 0.25. What I need to do now is determine what's going on with the graph at these two vertical asymptotes. So I want to see whether my arrow should be pointing up or down as I'm coming into each of these asymptotes. Okay, that's what I'm going to try to determine. So I'm just going to use my calculator here to do that. So I'm going to go press the y equals button, make sure all of my plots are off. And then I'm going to type in my function exactly as it appears. To get the fraction, what I like to do is press the alpha button and then the y equals to bring up this fraction menu. And then choose the numerator over divisor or denominator command. Oops. Okay. So there's that. And what I'm going to be interested in is what's happening right around the values of 2 and negative 2. Specifically, what's happening right before 2 and right after 2. So I'm going to go ahead and do a standard window. So I'm going to press the zoom button and select Command 6. And what I'm going to do is I'm going to look at a series of values. Now, the graph is basically telling me what this thing should look like. I'm going to pretend like I don't actually know this. So what I'm going to do is I'm going to press the vars button, go over to yvars, select the function option, and select y1, which is where I put my function, and pick some values that are getting progressively closer to 2 from like the right hand side from over here. So let's say I start with 2.1, and then I go to 2.01, and then maybe I go to 2.001. And if I look at that, we're getting progressively bigger and bigger and bigger values. So what my function is doing then is going to be doing this. So it's got to be going up as I get closer and closer to that asymptote, and then decreasing as I get further and further away of my asymptote. And I know it's going to be bounded in between the end behaviors. So it's going to start following that horizontal end behavior here. Now let's see what's going on the other side. So here I'm going to be looking at maybe 1.9, and then 1.99, and then 1.999, and I see that I'm getting progressively smaller and smaller and smaller. So what I can ascertain from that is that this part of my function is doing this. As I'm getting closer and closer to that vertical asymptote, things are getting smaller and smaller and smaller. I can do the same thing over here at negative 2. So let's look at the left-hand side of that. So negative 2.1. And then negative 2.01, and then negative 2.001. And you see again, we're getting smaller and smaller and smaller. So what that tells me is that as we're getting closer and closer to this asymptote, we're getting smaller and smaller and smaller. We need to be bounded in between those two asymptotes, so that part of my graph is going to look like this. And then the last piece is I need to see what's happening on the right side of this asymptote. So I'm going to do that. That'll start at, say, negative 1.9. And then we'll try negative 1.99. Oops, didn't mean to press that twice. And then negative 1.999. And here we're getting larger and larger and larger values. So it must be looking like this. So there's my first graph. And you'll notice that when I graph this on my calculator, very similar response, or matches what I got there. So symbolically, when we wrote that this arrow is going down, what we're calculating is the limit as x approaches negative 2 from the left, the negative side of it, where things are getting smaller, of f of x is equal to negative infinity, because the arrow is pointing down. Now, if we say are talking about this end, we'd say that this is the limit as x approaches negative 2 from the right of f of x is equal to positive infinity, because the arrow is pointing up. Now let's look at another example. New example. So first things I'd want to do is factor the numerator and denominator. Notice that since they're both degree 1 polynomials, there's really no factoring to do there. So we'll start by finding the vertical asymptote. I get those by setting the denominator equal to 0. Next thing, we'll look for the end behaviors. I notice the degree of the numerator is equal to the degree of the denominator, since they're both degree 1s. So what that tells me is that my end behavior is y equals the leading coefficient of the numerator, which is negative 1, over the leading coefficient of the denominator, which is positive 1. So my end behavior is at y equals negative 1. Next thing, we'll look at the zeros. To get that, I'm going to take the numerator and set it equal to 0. So when I subtract 2 from both sides, I get negative x is equal to negative 2. And I divide both sides by x to give me 2, which tells me I have the point 2, 0. For the y-intercept, I'm going to take x and plug it in, or x equals 0 and plug it in. So I have y equals 2 minus 0 over 0 plus 3. So I get 2/3, or the point 0 comma 2/3. Okay, let's draw our xy axis and get all this information on there. So we'll start by drawing in our vertical asymptote, which happens at x equals negative 3. And our end behavior, which is a horizontal asymptote, at y equals negative 1. I have the 0, 2, 0, and the y-intercept 0, 2/3. What I need to do now is figure out what's happening near this asymptote. So to do that, I'm just going to go ahead and type this into my calculator. So alpha y equals numerator over denominator. And then I'll type this in exactly as it looks. So 2 minus x for x plus 3. And then we'll do y1 of, I want things just on the other side of negative 3. So maybe we'll start with negative 3.1. So that's very negative. And we'll try 0.1, even more negative. And then we'll try 0.01. And even more negative. So what that's telling me is that as we're getting closer and closer and closer, we should be getting more and more negative, i.e. that the limit as x approaches negative 3 from the left of this function f of x is negative infinity. Now let's look at what's happening on the other side. So maybe we start at negative 2.9. That's positive. And then maybe we get a little closer. 299. And that's even bigger. And we'll try one more. Closer still. Oops. And we get even bigger. So what that tells me then is this part is pointing up. And I'll just kind of continue it through those 2 points and follow. Basically what we're saying symbolically there is x equal, or as x approaches negative 3 from the right, we go towards positive infinity. And there's our graph. Let's do one more example. Let's say that we want to graph y equals x squared minus 4x minus 5 over x plus 2. So I'm going to start here by just factoring the numerator. So I notice that that is factorable. Two numbers that multiply to give me negative 5 and add to give me negative 4 are negative 5 and positive 1. However, I can't do any reducing there, so we're okay. So the vertical asymptote, I'm going to take the denominator, set it equal to 0, gives me negative 2. Now for the end behavior, I notice that the degree of the numerator is greater than the degree of the denominator, because the degree of the numerator is 2, the degree of the denominator is 1. So what this tells me then is I need to do polynomial division. The nice part is, because the denominator is monic, I can just do synthetic division on this. So I'm going to do that rather than the long division. That isn't always the case, but it is in this case, so why make life harder than it has to be? So what this tells me is this part is the quotient y equals x minus 6. That's what I needed. Remember, this is the remainder part. We don't care about that for this. The remainder part doesn't really tell us anything. So the zeros, then we're going to take the numerator and set it equal to 0. And I'm going to use the factored version of the numerator set equal to 0. That gives me 5 and negative 1. So I have the point 5, 0 and negative 1, 0. And then the last thing I need is the y-intercept. So when x is equal to 0, I have y equals 0 squared minus 4 times 0 minus 5 for 0 plus 2, or negative 5 over 2, which is the point 0, negative 2.5. Okay. It's time to start graphing things, but before I do that, I need to make an XY table to graph this end behavior. So I can just pick values for X and find the corresponding value for Y. So I'm going to pick 0, which gives me the Y coordinate 6. And then I'm going to pick -6, which gives me the Y coordinate 0. You can pick any X's you like. I like to pick them kind of far apart because it makes it easier to draw a straight line. So first thing I'll do is draw in my vertical asymptote here at x equals -2. Next thing I'll do is draw in my end behavior. So my end behavior happens at 0, 6. Oh my goodness, look what I did, guys. Let's fix that real quick. Okay. Sorry about that. All right, so let's draw in those points. So 1, 2, 3, 4, 5, -6. 1, 2, 3, 4, 5, +6. So there's my other asymptote. I'm going to need to make that a little bit longer. Okay. And then I have my zeros, which happened at +5 and -1. And then my y-intercept here down at -2.5. And then I'm going to go ahead and see what's going on near this x or asymptote. Oops, wrong button. So we'll start just by typing this in. So alpha y equals numerator to denominator. And we're going to do x squared minus 4x minus 5 over x plus 2. I need to look where I'm going here because whatever reason I didn't want to do that. There's in the right spot. Okay, and we'll go out of there. So let's do the left-hand side first. So I want to see what's happening right after -2. So very negative. And a little bit closer. Oops. Even more negative. And a little bit closer still is even more negative. So what that's telling me here is that, use a different color. So here I'm going to be following this asymptote and then going down. And we'll do the same thing now on the other side. So there's pretty positive. Even more positive. Even more positive yet. So that tells me that the other end of this, or near the other side of the asymptote, we're pointing up. I'm going to go down. I'm going to go through those 3 points and then kind of continue following that other asymptote. So there's my graph. Okay, and our last example. So we'll start Obviously, I can see that there's going to be no reducing that can happen because I just have a plain old x in the denominator and there's not an x in every term in the numerator. So I'm not going to even bother with the factoring part. So my vertical asymptote is just going to be at the numerator or the denominator set equal to 0. No, that wasn't hard. The end behavior, I notice the degree of the numerator is greater than the degree of the denominator, so I'm going to have to do division. And I can do this with synthetic division. And since when I take the denominator and set it equal to 0, I just get 0. This is going to be a really easy synthetic division to do. So this part gives me my equation. Ooh, that's kind of strange that I get a quadratic there rather than a linear, but okay, we can deal with that. Next, I'm going to get the zeros by setting the numerator equal to 0 and solving. So here's a case where I guess factoring this numerator to start with would have helped, but we can do it all right here. So this I recognize as something that I can factor by grouping. So I'll make two groups. From the first group, I can take out an x squared. From the second group, I can take out a -1. Oops, that's just supposed to be an x. My apologies. And I notice now that each of these factors has an x plus 3 in common. When I factor that out, it leaves me with x squared minus 1. And x squared minus 1 I can recognize as a difference of two squares. And when I set each of these pieces equal to 0, I get -3, I get +1, and I get -1. So I have the points 3, 0, 1, 0, and -1, 0. And then if I do the y-intercept, again, I'm just plugging 0 in for x, but I know this doesn't happen because if I plug 0 in for x, I get a 0 denominator. I know, can't do anything with that. So let's get this information onto our graph. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. That's probably good enough. Okay, first things first, my vertical asymptote here. At x equals 0. Next thing I want to do is get my slant or my end behavior in. The problem is my end behavior is a quadratic. So to graph a quadratic, oops, I forgot the +3. We need a couple of things. We need the vertex, and then we need the 2 points on either side of the vertex. So the vertex is equal to the x-coordinate is -b over 2a. Thank goodness. Try to write things correctly there. And then whatever I get when I plug that in. So in our case, that x-coordinate is going to be -3 over 2 times 1, or -1.5. So -1.5 squared plus 3 times -1.5 minus 1, which gives us -3.25. Again, all I did was plugged in that negative 1.5 in for my x's. So I'm going to pick, say, -2, -3, and then -1 and 0. And I'm just going to do the same thing. So for -1, I get -3. And if you remember, if I pick the x-coordinates symmetric, so notice there's like a half a unit between -1.5 and -1, and also a half unit between -2 and -1.5, that those are going to have the same y-coordinates. And then we'll do -3 next, I suppose. So that gives me -1, and again, I have that same symmetry going on there. So to draw this asymptote, we're at -1.5 and -3¼ So we're down like there. I have -1, -3, and -2, -3, and 0, -1, and -3, -1. So there's my other end behavior. Yeet, that was not pleasant. Next thing I need to do is draw in my asymptotes here. So I have -3, -1, and then +1. Okay. So what I need to check for now is what's happening near this asymptote. So I'll go and I'll type this guy in. So I have x to the 3rd plus 3x squared, minus x minus 3 over x. And then I want that y1, and I want just on the other side of 0, so -0.1, and then we'll get progressively closer, so -0.01, getting bigger, and then 0.001, even bigger yet, so that tells me that on the left-hand side here, we're following the asymptote, and the other side's going to follow that other end of the parabola. And then over here, let's see how it's following on this side. So here we need positives. So I'll start with +0.1, pretty negative, and then 0.01, even more negative, and 0.001, even more negative. So I know that we're going to be following that end of my asymptote, or following the vertical asymptote going downward, and then the other end is going to be following like that side of the parabola. So the graph would look something like this. And that's it for this section. That was rough. So you'll have some homework assignment here. Just going to be practicing graphing things and finding the certain parts here. So let's do 1 through 24. And I'll have that on PowerSchool and everything for you also. Okay.